Martin Fowler said that any fool can write code that a computer can understand. Good programmers write code that humans can understand. This is a course about useful clean code principles. My aim is to teach you clean code concepts that you can use every time you write code. We use these concepts to create maintainable code that other programmers can easily understand and work on. The course has Java examples, and I sometimes mention things like Spring and Lombok. The same clean code concepts also apply to PHP, C# and Python. How can this course help you? It can save your company and yourself a lot of development time and therefore a lot of money. How? As time passes, bad code practices can make development very slow on your project. This means a lot of money wasted on unnecessarily long development time. This type of projects are also remarkably unpleasant to work on. This course helps you to avoid this by using clean code principles. The course is structured in 4 parts. The first section is the introduction, where we discuss what is clean code and why it's important. The second section is dedicated to small functions. I gave small functions an entire section because I think it's one of the most important principles of clean code, together with the related concepts of small classes, single responsibility principle, and not crossing different levels of abstraction. I saw that this is where developers fail most often when writing clean code. The third section is about fundamental principles. I discuss here about close to the code concepts like method and variable names, parameters, numbers and type, comments and exceptions. In the advanced principles section, I talk about more abstract topics. Things like the difference between an OP object and a data structure object, composition over inheritance, symptoms of bad code, state, low coupling high cohesion, command and query separation, tell-don't task, the law of Demeter and more. This course also contains some memes, because you can't spell clean code without fun. I try to stick to the useful things that you can use every day when programming and stay away from barren theory. There's no point in wasting time with useless knowledge. Knowledge that would just seem like it's helping you as a programmer, but that you will forget in 2 weeks. If that would be the point, this would be a 10-hour course about programming patterns, but it isn't. Hello, welcome to my course on clean code. I am very passionate about this subject, and I will explain why in a moment. First, what is clean code? Wiktionary defines clean code as software code written in a systematic manner so that another coder can easily interpret or modify it. Clean code is all about seeing your code through someone else's eyes and writing it so that they will understand it the first time they read it. So why am I passionate about such a subject? Well, I've been searching for clean code years before I knew it existed. Years before I knew it was called clean code. After programming for a decade or so, I felt like I was missing something. I saw a lot of styles of writing code, but some seemed to be more beneficial in the long run than others. I knew that there had to be some place you can find these rules, but I just couldn't find it. I wanted to take the next step in writing code, but wasn't sure what it was. For a while, I thought that programming patterns was what I was looking for. Everybody says patterns are the next step after you mastered basic programming. Most of the time as a programmer you program. And when you program, you create functions, classes, variables, use conditional statements and loops. That is what a programmer does 90% of the time. Every time you write a line, you ask yourself things like, should this method be smaller or bigger? Does it have too many parameters? Is the name of this variable too long? Can people understand this if, this for? Should I even care if they do? Patterns did not answer these questions at all. They had their value, but you use them very rarely, compared to making functions, for instance. So I kept searching until I discovered clean code in a video made by Uncle Bob. I couldn't believe it. It took years of searching, but here it is. What I was searching for existed, I found it, and it was as extraordinary as I expected. Most of the rules of clean code I already discovered by myself, but it still felt good removing doubt. Also, it was a nice feeling remembering tens of arguments about code and finally having confirmation I was right. My search was complete. I no longer had to be in doubt when I wrote code. The difference between art and science is that one is based on subjective experience and the other on objective knowledge. My code was no longer art, it just became science. This is Prometheus. He stole fire from the gods and brought it to humans. An action more or less comparable to what I am doing now when I am teaching you clean code. My name is Liviu. This is a picture of me when I'm not programming. I've been a programmer for 13 years. I have 10 years of PHP experience, 2 years of Java, a year of Python, and nobody is safe from JavaScript. I discovered when I started that if you program a certain way, it will be easy for yourself later to maintain that code. It enabled me to finish my task faster. It helped me to reuse a lot of my code. After I discovered clean code, I discovered that I was not alone. There are actually a lot of people like me. There is a science, because it is a science. You can learn it. It's not an art. It has rules, and if you follow these rules, you will write clean code, easy to maintain code. Martin Fowler said, "Any fool can write code that a computer can understand. Good programmers write code that humans can understand." I agree with him, and actually I've met a lot of these fools that he's talking about. I've met starters and juniors who wrote code difficult to work with, but that's normal. First you learn how to tell the machine what to do, then you learn how to tell the people that work on your code what to do. Sadly, I've met seniors, team leaders that seem to lack some sort of empathy. They couldn't understand why writing code in a complex way would make it hard for somebody else to work on it. Or they seem to think it's everybody else's fault for being stupid. Some of them were very intelligent people that wrote unintelligible code. Their code either killed a project or traumatized it for life. They didn't write clean code, they didn't keep things simple, they didn't think about the person that comes after them, or even worse, they tried to show off. You had to either rewrite their code, prepare to be very patient, or find another project or job, because it was hell maintaining code written like this, especially after a few months. There is a mean joke about stupid people. When you are dead, you don't know that you are dead. It is difficult only for the others. It is the same when you are stupid. The same joke can be made for people that don't write clean code. They don't know they don't write clean code, and it's difficult only for the others. Somebody said, "Always code as if the guy who ends up maintaining your code will be a violent psychopath who knows where you live." This is an exaggeration, of course. It makes very well, though, the point that you should care about the person that comes after you. If you wrote a line and I have to read it 3 times to understand it, you've done a poor job. When programming, you should keep asking yourself, will somebody that reads this for the first time be able to understand what I wrote? If not, to rewrite and simplify. The expensive part of projects is maintaining them. When you write new code, you have to maintain and understand the old code. If your code base is clean, it will be your friend and help you. If your code base is bad, it will be your enemy. It will even make you new enemies in the business and management teams. For example, small methods are very reusable and help you finish your task early with code that is already written and tested in productions. Large methods, on the other hand, is where bugs like to hide. So Grady Booch said, "Clean code reads like well-written prose." I had something like this in mind before I knew what clean code was. I was thinking that good code reads close to natural speech. Maybe I just haven't read enough well-written prose to say something so elegant. But yeah, clean code should be easy to read. You shouldn't see variables like pbag, statements like status not equals 1, and all sort of other unholy code. Please don't do that. We should leave our children a world full of beautiful code and not a bad code dystopia. Let's look at a little bit of code. I would not like to maintain this sort of code. It has a variable pbag. I don't know what a p-bag is because the person writing this was too lazy to use words and he only used the letter. And if p.sts is 1, what is sts and what is 1? He left a comment here, great. But I shouldn't be reading comments. I should be reading code because comments can lie, like we will discuss later in this course. So the process status is 1, which means it's running, and the process bag contains the process. Okay, so now I have to read the variables again and figure out how the comment applies to this code. I am not happy maintaining this code. Here is the same code written in another way. If process is running and process contains process of process. Okay, so there is a process bag, and if my process is running and that process bag contains the process, you want to set the status of that process to stop, and you want to remove the process from the process bag. Okay, starting to understand now. I don't have any comments. I have words that explain to me what these methods do. I'm starting to be okay with this code. Actually, very okay. I could maintain this. Another way of writing it would be like this. If the process is running and it takes 2 parameters, he probably looks for this process in the process bag. Okay, I understand this. He wants then to kill the process and he wants to change something in the process and probably remove it from the bag. Okay, I understand this also. I trust the methods do what they say they do. I don't want to see the implementation details now. If I'm debugging and I see the bug is hiding in one of these methods, then yes, I will take a look and see what is going on there. But I understand a lot of functionality as much as I need to very fast. I like this. I can maintain this. I like it so much I prefer the third example of code with bugs not working to the first example. Because what the hell is going on in the first example? First of all, I don't understand it. I will have to rewrite it. The third example I understand. I don't have to ask somebody else. I don't have to take wild guesses. I feel comfortable working on code where it's very clear what the programmer was trying to do. All these code instances work. The machine understands them all, and it doesn't care which one you wrote. Humans care, and they care a lot. I think keeping functions small is the most important concept in clean code. Same goes for classes and packages. You can also apply this to projects and you'll find yourself working with microservices. But that's beyond the scope of this course. But it is very important to remember this for functions. Keep them very small. Small functions can defeat overwhelming complexity in big projects. I will discuss mainly about small functions. Functions is what you will work with most of the time. So why do I think small functions is a good thing? Doesn't that make them like harder to see or something? Well, small functions have several advantages. They are easy to understand, maintain, debug, reuse, test, and keep bug free. They help you avoid code repetition, they beautify code and separate concepts into their levels of abstractions. Let's discuss about each advantage with some code example. In this episode we'll discuss about small functions being easy to understand. So, small functions are easy to understand. Let's look at 2 functions that do the same thing. They get called from another class, they have the same parameters, and return the same result. It's a big decimal. We have the first instance of the function. This is not a big function. The body of the function has 6 rows, but it's really smaller than that because it has very little complexity. 4 rows are just parameters arranged so that they don't extend to the right too much. This counts as 1 row. we declare a variable and return it right away. This also adds one row, but it makes things clearer. It doesn't obfuscate, so we might as well not count it as complexity. I would say the complexity of this function is 2 rows really. This is very small. But what does this function do? Mainly it calls another function, get previous rank of value. There is a programming concept called single responsibility principle. According to it, a function should do only one thing. Calling other functions is not a thing. What else does this function do? Well, it calls yet another function to calculate a soon-to-be parameter, price by trade type, which is used here. This is not a thing either. It also declares a variable and return it right away like we discussed. You have to set some special settings in IntelliJ actually, so that this isn't highlighted as a mistake. Why do I declare this variable and return it right away? For 2 reasons. It's the easiest way you can set a breakpoint to see the result without exiting the function. Of course there are other ways, but they're a bit of a headache. And it makes it more clear that a change of conceptual level happens here. My caller wants the stop loss. This is why it's in the name of the function. This is a term in stock market. It's a price at which you would sell your asset to stop losing even more money when the market goes against you. So he wants the stop loss. I create this variable to make it very clear that the stop loss will be the previous rank of value from now on at this conceptual level. Well, at the next conceptual level actually. You can imagine when you write code that somebody is pointing a gun at you. You want to make very slow moves to make sure he understands everything that you are doing and that you are not posing a threat. This way he doesn't shoot you. If he would look at the stop loss and all of a sudden I will be talking in my code about previous rank of value without him noticing what happened, I might startle him and end up shot. So this function almost doesn't do anything, but it has enough complexity, half a thing here, half a thing there, to justify its existence. I don't know everything that happens beneath it, but that's okay. If we wanted to see everything a function does to return its result, line by line, we would have to put all the code inside it. Imagine what our main functions would look like. Basically, they would be the entire project. It did tell me some things. It showed me what I will use to get the result as parameters for get previous rank of value function. It also showed me that in this strategy, this packet is a strategy for buying and selling assets, let's call them, the stop loss is the previous rank of value. This might be the only thing we wanted to know. If it was, we will be finished now. Okay, why not just call get previous rank of value function one level above? Well, one level above, the code only cares about the stop loss. It doesn't want to know notions like previous rank of value. It isn't coupled with most of the rank of stuff, and we want to keep it that way. Coupling is bad, and I will talk in a later episode about this. Also, this small method extracts some of the complexity that otherwise would be at a higher level. Well, okay, enough about the first function. Let's talk about this second function, the big function. Let's read it once, very fast, like we did with the small function. Okay, I don't understand anything. It has 2 ifs, it throws an exception at the end, there are some Renko stuff here, some extract and multiply. It's just too much to understand what it does. I will have to read it again very carefully, and maybe again. And again. Imagine if I only wanted to know how the stop loss is obtained here. Is it clear that the stop loss is just the previous rank of value? Not at all. That information is lost in all these details. As you can see, all kind of different things happen in this function. The exception line at the end is quite big. It shouldn't go so far to the right, but it does. Why didn't it bother me earlier when I was looking at the small function? Well, because it wasn't there. I didn't have to put up with it. The smaller the function, the smaller the chance for weird stuff to draw your attention. I have to read it a second time. This is just not easy to understand. It's more complex than usual code, but I can defeat that complexity with well-named small functions. Like small David defeated giant Goliath. Small functions defeat giant complexity. They encapsulate it. They are like signposts that act like clues. So this second function is big. Its body has 11 rows. But these are some complex rows. So complex, I won't even go row by row over it. You might say, but Liviu, if I concentrate a bit, I can understand what is going on here. Well, you shouldn't. Programming is simple if you write clean code. Making programming hard is not smart. You will find during your day problems that need creative solutions. Keep your focus available for those. You only get a limited amount of mental energy per day. I don't want to read code 2-3 times to understand it. I don't want to think when I program. Like I said, programming is simple. Keep it that way. You might also say, hey, 11 rows aren't that many, I've seen much worse. I know, me too. I've worked on projects with people that thought 100 rows are the upper limit for a function. So yes, I know, it's hard. I will keep my statement. This function is big. What is that you say? Comparing these two functions is not fair. I should compare the big function to the get previous rank of value. Okay, let's do that. Okay, let's look at get previous rank of value. First of all, notice the concept of stop loss disappeared. There is no stop loss here. We are now at another conceptual level. We are now in Renko world. There is no stop loss to worry about. By using small functions, we are able to separate the conceptual levels. I also noticed that trait type is used in two ifs. It takes two values and acts a bit like a Boolean parameter. That's not very good. But we will talk about Boolean parameters later. So let's read very fast get previous rank of value. It has two ifs. Okay. And throws an exception. Suddenly I can focus on these ifs because there isn't much else like there is here. It's very clean. The first if treats the case where the trade will be making money if the price will move up. The previous rank of value in this case will be the price minus a number of boxes. Okay. And for the price moving down, the previous rank of value is the opposite. Okay. The price plus a number of Renko boxes. It's still relatively hard to read code, especially when you don't know what Renko is and the context of the project. But I sort of understand what's going on. Didn't have to read it twice, didn't have to focus very hard and prove anybody that I'm smart, didn't have to read more information than I needed. It also throws an exception for the case where the price isn't moving up or down. Okay, that makes sense. Let's look at the big function. No, I still hate it. I don't understand it. I don't want to understand it. It takes too much energy to understand, even if it basically does the same thing. I don't want to maintain this. But we are still not at the last level of the function stack. Let's compare this big function to get price minus Renko boxes. By the way, notice again how small functions act like signposts in your code. They give you directions and clues to what is going on and where you should go. You don't have that in big functions. Let's take a quick look at getPrice minus Renko boxes. So it deals with the price and the number of boxes parameter. Okay. It creates a Renko absolute value per box from the current price. Okay. It transforms number of boxes into a big decimal. Okay. Using that absolute value per box and the number of boxes decimal, it creates an absolute value to subtract. Okay, it wants to subtract. It uses the price minus that value. Okay, I understand this. I only had to read it once. Imagine having a bug here. Would you prefer to read this code in the upper method or this code in the lower method? Well, I know for sure I would prefer to work on a bug here. Okay, let's analyze the big method now, line by line. You should know me by now, I'm not going to do that. It's unnecessarily hard, it's stupid. Let's have a quick look at the same small function as before, but made even smaller. Actually, I can even make it a one-liner. I think IntelliJ recommended me to do this. Finally, I'm writing clean code. This is a lot easier to read because it's small, right? Well, wrong. Please understand, this is wrong. Small number of characters and small number of rows doesn't automatically mean smaller complexity. Small number of characters and small number of rows don't automatically make the code easier to understand. Let's look at it. First, we do the same thing. We assign getRenko absolute size to a variable, just like in the second case. This actually helps. This makes the next row a bit easier to read. I could have added this row inside the monstrosity of the next row, but I just wanted to show that this tames a bit the beast. The last row returns. This is kind of already one thing when you return. But we also subtract something from the current price. We subtract the Renko absolute size per box multiplied by number of boxes made into decimal. What? This is too much to understand easily, sorry. As a rule, only do one thing on a line. Only one statement, only one assignment. Remember, imagine that somebody is pointing a gun at you. If you do more than one thing at once, you might get shot. If it's not very clear what the result of your action is, you might also get shot. Now let's look at the second instance. It is bigger, but every row is very clear, almost too clear. What I'm doing here is complex. I don't want to confuse the reader. This type of variables are like function names. They are like signposts and clues in your code. Recommending small functions is about recommending complexity. Adding rows that increase the function size in this case actually decreases complexity. It makes it easier to read. IntelliJ will by default suggest you remove some of these variables. It considers them redundant. But sometimes this kind of redundancy adds clarity. To turn off that IntelliJ suggestion, just press Alt-Enter on a variable he's suggesting removing. Select inline variable and edit inspection profile setting. You have a checkbox there called ignore immediately return or thrown variables. Check it. Just to satisfy my OCD, let's look at the last level in the stack and compare these two methods. So what does this method do? It multiplies the price with the Renko default relative size. I'm guessing it's some sort of value between 0 and 1. Okay, I understand this. Yeah. I hear you there in the back. Come on, review, isn't this function too small? No, this function is not too small. This function is not too small. This function is not too small. This function removes complexity in the place where it is used. I would have to see the price is multiplied by some constant and having to understand it is some sort of Renko absolute size. It is easier if I get that message from the function name. The function name acts like a clue, like a signpost. I'm repeating this a bit because I want to make this very clear. Replacing a small piece of code with an easy to understand function name is called beautifying the code. I encourage you to do it when it makes sense. Of course, when the row that you are removing is a bit complex, that's when it makes sense. It helps you read the code like natural language. It helps you read the code like well-written prose. Now, let's read the big function. Of course, I'm not going to read the big function. That's not programming, that's just hurting yourself. Why are you hurting yourself? Stop hurting yourself. You might be tempted to say that looking through 4 small functions take the same time and energy as looking through one big function. Please don't. No, don't. I'm not going to even pretend that might be true. Complexity feeds upon complexity. If you put 3 things together, you will end up with more complexity than just their sum. Complexity emerges from complexity. Also, you don't have the small function names to guide you. You just have code upon code, angry and eager to fight you. Don't choose the way of pain. Okay, we will continue in the next episode about other advantages of small functions. Last episode, we talked about how small functions are easy to understand. Let's talk about other advantages. Small functions are also easier to debug. I'm more comfortable debugging the first function than the second one. You don't have the big scope to worry about. Maybe you will play a bit detective until you find in what method the bug is. Function names will help you to keep track of where you are. But once you do find the buggy function, you'll only have a few lines to move the debugger through. It will be much easier spotting the bug. Small functions are easy to reuse. They are like Lego pieces. You can combine them in a lot of ways to create different algorithms. The first function does one thing. The second function does about 4 things. Which one do you think you can reuse inside a project? Well, of course, the first one. Let's imagine 3 small functions. We will call them x, y, and z. Each one of this function follows the single responsibility principle and only does one thing. X does A, Y does B, and Z does C. Now let's imagine a big function that does 3 things, A, B, and C. Okay, let's see if the small functions are more reusable than the big one. Combining X, Y, and Z, we can immediately have the W functionality. We didn't write any new code, we just use the methods. But there is more. We can also do AB without writing any functionality. If we wanted AB and we only had the W function, we would have to refactor it and make 2 smaller functions, one for AB and one for C. Or even worse, copy the AB functionality into a new function, which will duplicate code. Same goes for AC and BC. This is bad. The small functions also help us if we need A, B, and C alone. So 3 small functions give us 7 algorithms. Not to mention cases when we need something like ABCAA, for example. Like I said, small functions are very reusable and flexible. It is very unlikely, on the other hand, someone can reuse our big function. Because big functions are very particular. You have to need the A, B, and C functionality exactly in that order. That lowers a lot the chances you can reuse it. Because small functions are so reusable, they help you avoid code repetition. You can just call your methods for the desired functionality instead of being tempted to copy code. This also helps you have less bugs by allowing you to use tested code. Tested either in production or code that already has unit tests. Small functions are easy to test. In a small function, the test cases are obvious. Look at the first function. Just look at it. Let's pretend it's not static to simplify the discussion. It's easy to understand what it does, and it's very clear how to test it. We will not have to use a lot of mocking, spies, and whatnot. Our test will also be clear and small, just like our function. Now look at the second method. It is private and we shouldn't test it, but look at all that code. It needs tests. It craves tests. Feeling the need to test a private is a big clue you are breaking single responsibility principle. It's also a sign that this code should be extracted in another class. There it will be public and should be tested. But what are the test cases here? Well, for sure there's more of them than for the first function. It is a lot more likely to miss test cases in a big function, or to be demoralized and skip testing altogether. You'll also have more dependencies to worry about. Small functions are easier to keep bug-free. How many bugs can hide in the first function? How many bugs can hide in the second function? In a big function, you have a big scope. You have a lot of lines, and that can make you miss things. Big functions is where bugs like to hide. Small functions, on the other hand, also promote code reusability. This means you will use code that is already tested, so you'll have less chances to introduce bugs. Small functions beautify code. Price that multiply by Renko default relative size is hard to read and understand. Using a small function, we can remove complex statements and use something closer to natural speech to make it easier to understand. In this case, it's get Renko absolute size. So you see how price that multiply Renko default size is here, but there's also a lot more to worry about. You can just beautify it by using get Renko absolute size and everything will be easier to read and understand. Granted, this example is very particular to this Renko business. It is still a bit cryptic, but I think you get the point. Small functions separate concepts into their levels of abstraction. What are levels of abstraction? Well, in this case, we have a concept level that deals with stop losses. This is a stock market concept level. This level needs some statistical functionality like Renko charts. But statistics are one thing and the stock market is another. We can say there are different levels of abstraction. We need to keep these levels separated to decrease complexity. Small functions help us do that. Small functions are inherently good at not mixing different levels of abstraction because they are small. Like I said in another video, how many things can you do in 5 lines in order to cross levels of abstraction? The first small method is called from a function that has the concept of stop loss. It is separated completely from the concept of stop loss and the stock market level. It lives entirely in the statistical level with the Renko concepts. The second method, on the other hand, mixes both the stop loss concept and the Renko concept. It is crossing different levels of abstraction and that is bad. It has increased complexity, increased coupling and low cohesion. We will talk more about coupling and cohesion in a future episode. And finally, small functions are easy to maintain. This is sort of an emerging property. If a function is easy to understand, easy to debug, easy to reuse, avoids code repetition, is easy to test, easy to keep bug-free, beautifies code, and separates levels of abstraction, it will be easy to maintain. I am talking a lot about small functions. I am not being paid by the small functions elite to further their globalist agenda. Small functions, single responsibility principle, low complexity are the most important subjects in clean code and thus in programming. This is why I think it is a good idea to explore them in detail. We will stay a bit more on this subject in the next episodes with extracting functions, SRP and levels of abstraction. It is now time to talk about names. Names of variables, names of functions and classes. What parts of speech to use and what size the name should be. I will explain something called the scope rule for names sizes. Names matter a lot in programming. Even with small functions, if you have cryptic names, you won't be able to understand anything from the code you are reading. Names are the main tool we have to express intent. Method names tell you what a method does. Variable names tell you what a variable contains. What parts of speech should I use? Well, classes are nouns. Price, current trade. Don't be afraid to use technical words like service, component, repository, interface, abstract. For example, user service or user component, user repository. They look spammy, but in my experience, they save time. This is a bit of a controversial subject. I actually tried writing code for a while without these helper words, and I often found myself lost. I'm in a class called user. Okay, this must be a domain class? No, it's the service. Well, why not put service in its name then, instead of making me scroll up and try to figure out what class I'm in? Helper and manager must be given a lot of thought, and only be used as a last measure in distinguishing this class. Still, I prefer user manager to user. Plain user makes me think it's a domain object. User manager at least tells me it's not a model. Variables should be a noun. Price, current trade. Verbs would sound silly for variables. Think of a variable called start trading. What would it contain? At most, a Boolean. We will talk about Boolean in a moment. Or maybe it has a function inside it. It's weird to think of it as being a float, for instance, start trading. It's like something is missing from its name if it's a float. You want to imagine its correct name as being something like start trading threshold. That I understand. Booleans are predicates. Is scheduled, is running. They feel natural in if statements, like if process is scheduled, do something. If process is running, do something else. Methods should start with a verb. Get strategy result, create strategy result. Methods that return a Boolean should be a predicate, just like Booleans. Is scheduled, is running. Your getter should start with get, don't make them nouns. That is a horrible habit. It looks confusing. Confusing is the opposite of what we're trying to do when writing code. And nouns should be adjectives. What about the size of the names? How big or small should a variable name be? I've had this discussion many times, especially since I like very descriptive variable names. Uncle Bob talks about something called the scope rule for variable sizes, which makes a lot of sense to me. If a variable has a small scope, it should have a small name. As long as you can see its declaration 2 rows above, I kind of understand what it does. If a variable has a big scope, it should have a big name. Obviously, this variable is not easy to track, so it should describe itself very well, if it has a big scope, that is. The opposite is true for functions and classes. The bigger the scope, the smaller the name. The smaller the scope, the bigger the name. The idea behind this is that you don't want to have public functions used everywhere with huge names. It gets confusing and it's spammy. You want often used public functions with small names. Also, for small scope private methods, you want a big descriptive name. For example, extract file and output contents. Private methods are only used in their class, and usually only once. This means they have a small scope, so they should describe exactly what they are doing. It's okay if they have big names. You won't see their name often, and you will know exactly what they do. Let's look at some code. The I variable is a convention in programming, but it also follows the scope rule. It is usually used 1 or 2 rows lower than its declaration, so it's okay to be 1 or 2 letters long. Even if it's not used immediately after, everybody would expect the I variable to be the current iteration. So it follows the spirit of the rule. If a variable is easy to recognize, it's okay to be small. I personally don't like variables that are not at least one word except for I or J. That mandatory government tax variable comes out of nowhere. It's probably declared somewhere way above. The second part of the scope rule says that if a variable has a big scope, it should have a big descriptive name. So there it is. That variable doesn't keep any secrets from us. What not to do when naming things? Small names. I often see programmers thinking that if they use very small name variables like tr or td, they will make the code easier to read because there is less of it. That couldn't be further from the truth. It's very hard to express intent using a variable like tr or a function name like dd. Even if it follows the scope rule, I will still promote it to one word. Names that are not real words. They are not small, but only the programmer that wrote them knows what they mean. Another error would be methods that are nouns. There's some sort of need for some programmers to break the rules. They express it using nouns for their methods. Don't do that. User is not a method name. Delete user is. This is true for setters and getters also. The only place where I accepted this was for setters in a builder. This seems to have become some sort of standard and it's too much of a bother to change it in Lombok. Naming is the best tool we have to express what we do. It is almost the only way to show our intent. When you name things, think of the person that comes after you and maintains your code. Ask yourself, how should I name this variable to help the person reading my code understand what it contains? How should I name this function to make him or her understand what this function does? Through names is how your code talks to the programmers reading it. Through names is how you talk to the programmers reading your code. Names are clues and signposts in your code. They guide programmers and help them arrive at their destination. Don't be afraid to make names descriptive and meaningful. How many parameters should a method have? The answer is the fewest possible. Maximum 3, preferably 0. Arguments are bad. Each argument brings more chaos into your function. Each argument increases the complexity of your method. The more arguments your method has, the harder it is to use. Especially dangerous are the same type arguments. The more same type arguments your method has, the easier it is to confuse them and create bugs. Another category of parameters you especially should try to stay away from are parameters passed by reference, that change state inside your function. You risk modifying the state of objects where no one expects you to modify it. That is, far away from where it should be modified and where the state is used. If you can't avoid changing the state of parameters, at least make it clear you are doing so. You can do this by returning that parameter. If you can't return it, you can show this change with the name of the function. If this is also not possible, as a last resort you can use comments. We will discuss in a future lecture why using comments is bad and why they mean you fail to express yourself with code. So it is best to avoid changing the state of your parameters. In the first code example here, we signal very well that something happened to the result, including by using a new variable. There is an issue with it though. If we return the result parameter and we added the HTML directly to it, some poor programmer that comes after us might think the old result doesn't have the HTML part. Situations like this is where I recommend to stay away from changing your parameter state. The second example is okayish. It defines very well what it does and reads very easy. There is still a chance someone might miss that something happened to the result. I like the third example more. It signals very well that something happens to the result variable. The fourth example is terrible. A lot of things happen and no one will expect that result changes inside that function. This is the kind of function you should not write because it leads to hard to find bugs. Changing state is important. You should make it as clear as possible when you are doing it. Your code should scream, "Hey, I changed the state of this object inside my function, be careful here." Arguments also couple your method to the outside. The more parameter your method has, the more coupled it is. What if I need many arguments? I need to pass 5 different strings. There is no way around it. Create a new class then. The fact that these variables are sent together means they have enough cohesion to be together in a class. If you can't find any good name for what they represent together, just add an input at the end of your function name. I like to make this type of objects immutable, so I only give them getters and a builder from Lombok. Well, as immutable as possible anyway. That way you can create the object, but nobody will try to set its contents. He can still change it, but you send a clue that he shouldn't. You can make it an inner class or put it in the same package or create a package just for these types of parameter classes if they don't seem to belong anywhere else. All of the things that I said until now also apply to constructors. It is common for constructors to take many arguments. In this case, you can either create a parameter class or use a builder. What do you think about Boolean parameters? Never use Boolean arguments. If you use Boolean parameters, it means you are doing more than one thing in your method. Also, it's hard to figure out what a Boolean argument does. IntelliJ actually helps now by showing the parameter's name at the calling place. Instead of using booleans, create two methods, one for true and one for false. What do you think about null arguments? Null arguments are just like booleans, so the same rule applies. Create two functions, one for null and one for value. Only expect to receive null when the users of your methods are outside of your team. Checking all arguments for null is called defensive programming. It should not happen inside the team, only for public APIs. We talked before about how small functions beautify code. Small functions can replace complex statements with an easy to read function name. This is especially true for predicates. Predicates are what is between the parentheses of an if. Sometimes they get complex and hard to read. Instead of making the readers of your code decipher your cryptic if statement, you can replace it with a function. This will make the code easier to read and is called beautifying predicates. We looked at an example in the introductions video. Don't make the maintainers of your code read the first if. It is harder to read if process get status equals status running and process bag contains process. It's more natural to read if process is running. The first statement here is still readable, but it can get a lot worse than this. When the if statement repeats itself, then you have even more reasons to encapsulate it in a well-named function. I'm a big fan of beautifying predicates, and I wish the same thing to you. Should I write comments? I like this subject because it's counterintuitive, especially for starters. What do you think about comments? Don't tell me, just think about it. I won't be able to hear you anyway. Comments must be good. I mean, they explain the code, and code is not easy to understand. Just the developers don't have the time or are too lazy to write them, right? Wrong. Comments are bad. Why are they bad? Comments are bad because you can't trust them. They might be lying. There are only two things you can trust in programming: code and tests, which is code but different. The best way to transmit to the reader of your code what your code does is through the code itself. Use smart variable and method names, use the scope rule, beautify predicates, use the correct parts of speech in your code. Code doesn't lie, code doesn't rot, code is always true, it does what it says it does. I'm not talking now about poorly named variables, but about the fact that code executes exactly what is written. Comments don't execute anything. It is likely that comments might be true today and false tomorrow. The reason for this is that when the code changes, the comments don't have to. It might not even be the developer's fault. If one class has a comment saying that another class does something, when the developer modifies the second class, he won't know about the comment in the first class. Because you can't trust comments, they become something like spam. You already have to read code to figure out what's going on. You don't want to read comments too, to understand the same thing you just read. Or even worse, you can get wrong information because the comment is no longer valid. If you put comments everywhere in your code, people will just start to ignore them. If they are rare, for sure they will be scared when they find them and they will read them. This is important because sometimes you do need comments. It's okay to write a comment when you absolutely can't express yourself with code. For instance, when you write a regular expression, you might want to leave a comment behind explaining it. A variable name is too short to explain a regular expression. Also, when you want to warn users of bad consequences, like if you set this flag to false, the cron will not be executed and people will not be able to work in the next morning, then it's okay to leave a comment behind. There are also to-do comments. Yes, ideally you should not leave to-dos behind, but life is not always perfect, so to-dos happen. You should write detailed comments when you write a public library. These are valuable comments, especially in the form of Javadocs. In general, when people outside of your team use your code, you might consider comments, depending on the situation. Javadocs are comments. I don't know why so many developers are shocked by this, and they refuse to believe it. Javadoc follows the same rules as the comment presented here. Try to get as far away as possible from people that will try to force you to write useless Javadoc. You are not in good company if you have them around. Comments should be readable in code. Don't put links, HTML and other tags meant to make the comments look good when exported. Most of the time comments will be read in code, and that's where they should be easy to read. Now let's talk about especially bad comments. If you see comments that lie, either fix them or delete them. Always delete commented out code. I can't believe this is still a thing in 2020. We have Git and IDs with history. We don't need commented out code. Maybe there is the rare case when a flag or some other one line that changes often is commented out. Rather than have your team revolting against you, maybe it's better to leave it. But never allow methods and lines over lines of commented out code to exist. Delete comments that are obviously useless. How do these comments help me? What is going on? Why do comments like this exist? These were just some examples of bad comments, but as a general rule you should avoid comments. Sometimes you might not be able to avoid them, but you should feel bad about writing them. Writing comments means you failed to express yourself in code. I spoke before about how in object-oriented programming, objects in code map entities from real life. These objects map their feature and current status in properties and state. They take their internal actions in private methods. They take their external interactions in public methods. When working with frameworks and ORMs, the object that has properties and state comes from the database. Frameworks and ORMs warn you that you shouldn't encapsulate behavior in these objects. They should be as dumb as possible and just map the table from the relational databases or document from non-relational ones. Because of the way frameworks and ORMs work, there is no point fighting this, and you have to accept that these objects will be dumb. By dumb, I mean they don't have any behavior, they don't have any functional logic, they just can't do things. For example, a real-life dog does things. Let's say he plays with a toy. A dog object from object-oriented programming also does things. He plays with a toy using a public method play with toy. A dog from the database knows when he played the last time, but he can't play. The service plays for him. In frameworks, you naturally put the behavior in services that are singletons. But a contradiction arises here. We use the name objects for this last category, but they only have state, they don't have any behavior. They seem to be objects and yet they are not. And this is true. They are objects because this is the representation we use most often for them, but are something different from the object-oriented point of view. They could do their job just as well with arrays or maps. They are data containers, data structures, data holders, bags, or whatever you want to call them. They only exist so that our data has a body to live in. Like I said, we could as well use arrays or maps. It's just more convenient to use objects. From the object-oriented point of view, they are not objects. So we will see in code two types of objects. There is the classic object from object-oriented programming. Inside such an object, you should avoid writing getters and setters. You should encapsulate your state and only expose what you really have to. You should use tell-don't-ask to get things done with objects. We will discuss tell-don't-ask in a later episode. getters and setters also attract coupling. This is because a lot of objects will know the internals of your object, things that maybe they should not know. That is because they can find out everything about it using getters, and they can change its state in any way they want using setters. Instead of classical getters, you might want to return information in a more informative way. For instance, instead of get last time dog played, you can have something like is happy. This might not be one parameter. It will encapsulate some behavior but exposes something that the system cares about. Other objects don't need to know about your object internal mechanisms. They don't need to know that you have a last time dog played property. What they really care about is if you are happy or not. Besides reducing coupling, it is also easier to refactor. You decide you should store your playtime in some other way, no problem. The isHappy method will still work, so the external system will not change or need to know something changed. You will only be touching your own class because your state is encapsulated. The second type of objects are the data structure classes or data holders. These are objects that hold data. For example, objects holding a row from a database, objects that map a JSON, or data transfer objects. This type of objects are the opposite of traditional objects. They should have all their state exposed and they shouldn't encapsulate anything. At most, they should have methods for providing their data more convenient, like get full name besides get first name and get last name. I know developers that leave this kind of objects without setters and getters and just have their properties public. I've tried this for a while and didn't find any major problems with it. So, don't be confused the next time you see a data object and feel like encapsulation and entity behaviors are missing. Remember this distinction about real objects versus data objects. There are two main ways an object can interact with another object. It can have the other object as a property, this is called composition, or it can inherit the other object, this is called inheritance. Composition over inheritance is a programming concept stating basically that composition is preferred to inheritance. I will not talk about the polymorphism aspect of this to simplify the discussion. The reason for composition being preferable to inheritance is that inheritance leads to rigidity, while composition leads to flexibility. One of the few useful things I learned at university was object-oriented programming. I understood the concepts rather well, and when I began working as a programmer, I started using these concepts. Back then, I was using PHP and object-oriented programming was optional, but I was a big fan of object-oriented programming, so naturally I wanted to use inheritance. I was lucky enough to work alone on a lot of medium-sized projects, so any mistake or bad code I wrote turned against me. It was easy to see what was maintainable and what was not. There was no one else to blame, all the mistakes were mine to learn from. All the clean code and good practices were also mine to understand and reuse. I started using inheritance a lot. I thought it was a good way to write code and one of the best ways to avoid code duplication. And I was wrong. After a month or two on the same project, this became obvious. That's about the time when I would want to inherit more than one class, which is not possible in PHP, or Java or C#, and this is a good thing. This was the first sign that inheritance was turning against me. After a few more days, the second sign would appear. I had children that needed some of the parents' methods, but not the others. The solution was simple, right? No, I'm not talking about some sort of partial inheritance that violates the Liskov substitution. The Liskov substitution principle says that children objects must be able to replace parents in an application. If you ever saw a method, something like throw exception, not implemented in this child class, you saw a violation of the Liskov substitution. There are some complex reasons for why this is bad, but just the fact that it's incredible, unexpected is enough for me. A big part of clean code is to be predictable. So the correct solution was breaking the parent classes into multiple smaller classes to make them more flexible. Splitting inheritance with multiple levels is not something pleasant. It also destroyed my system of abstraction of reality. This was the third bad sign. For example, let's say I started with a dog parent class. After I had to split it, I ended up with 3 different classes: food eater, ball chaser, and man's best friend. This had almost nothing to do with the reality I was trying to abstract. My new classes on the tree no longer belong there. The inheritance chains became hard to manage, and I was not sure where a class should fit. I did this in 2 or 3 projects until I finally gave up and accepted that composition was superior to inheritance. Inheritance is a great concept in theory, but in my experience and in the experience of many programmers, it fails in practice because of rigidity. This is why we have this programming principle, composition over inheritance. I will show you a simple case when composition should be used instead of inheritance. I know this is a very obvious case and nobody would use inheritance here, but it doesn't affect the point I'm making. In my experience, if you use inheritance when you should have used composition, there will be hell to pay in the medium term. If you use composition when you could have used inheritance, nothing bad will happen. I can't think of an instance where I thought someone used composition when they should have used inheritance. This is counterintuitive when abstracting the world into code, but it gets obvious when the project grows. The bigger your inheritance chain will grow, the more could have used inheritance turns into should have used composition. This is because of the rigidity of inheritance. But let's see what happens when we use inheritance when we should have used composition, to give a simple, clear example. We start with a horn class that can horn. The business team asks for a car class. All that this car can do is to horn, so you make it a child of the horn class. In this example, it's obvious why this is wrong, but when not working with such clear concepts like car and horn, it's more fuzzy and you can make mistakes like this. After 2 or more sprints, the business team asks us for a steering wheel and the car should be able to steer. I got to this point a few times when using inheritance. The answer is obvious, we switch to composition. It's a lot more simple if your car has a horn and a steering wheel instead of trying to be a horn and a steering wheel.